Okay, first, I'd like to thank organizers for inviting me to this Strings 2011, which is extremely wonderful meeting. So here, I'd like to talk about recent developments about holographic entanglement entropy. And finally, I'd like to mention some new extension of AdS CFT, which is closely related to this quantum entanglement or entanglement entropy. So before I go on, I'd like to thank my collaborators listed here. So the contents of my talk is like this. So we first give some motivation why we consider entanglement entropy and its relation to the quantum gravity. And I explain how to compute entanglement entropy by using holography or AdS CFT correspondence. Now I'd like to apply this method to investigate gauge theories such as confining gauge theories, and also discuss our recent result about how to incorporate higher derivative corrections. And then I'd switch to the another issue, but which is closely related to the quantum entanglement, which is a new extension of AdS CFT, which I call AdS BCFT. And by using this idea, I'd like to mention some recent attempt towards the construction of holographic dual of lattices, lattice points. Now, let me begin with introductions. As we know, or we're very familiar with, the holography, or especially AdS CFT correspondence, offers us a way to understand non-perturbative definition of quantum gravity. So we have some bulk, which is in my convention d plus 2 dimension, and which is actually equivalent to some, this bulk is some gravitational theory, but actually this theory is equivalent to non-gravitational theory, which lives on this boundary, which is d plus 1 dimension. And in physical language, their partition function is equivalent, as we know. To explore the holography, especially in general space-times, general setups. So here I mean not only AdS, but also including flat spaces or de Sitter space, whose holography is still not completely understood. So then we need some suitable physical quantity, which should be a rather general or universal quantity. So to discuss stationary black hole, we know that the mass and charge and spin characterize a black hole because the system doesn't depend on time, and also the system is described by thermodynamics. But for generic spacetime, which is time dependent, we need some consideration about non-equilibrium dynamics. Then we need much more information or quantities. So here we'd like to argue that quantity, which called entanglement entropy, whose property and definition will be explained later, is a good and appropriate quantity. So let me quickly summarize the definition of entanglement entropy. So this is a very elementary idea, which is just in quantum mechanics. So we divide the quantum system into two parts, A and B, which we call subsystems. And the total Hilbert space is factorized into HA times HB. This is a direct product. So if we imagine spin chain, we just cut it at some point, just artificially cut it out. And then we can just define subsystem A and B this way. Hilbert space is completely factorized. We can do this same thing for quantum field theory, as I explain later. So the next thing to do is to define density matrix. And we know the total density matrix. This is just standard quantum mechanical quantity. So the rho tot is total density matrix. And we trace out this subsystem B. So the trace over Hilbert space of B. And then we get some density matrix for A. So this is so-called reduced density matrix. So we lose some information. We smear that information. But anyway, we get some matrix for A. And this is so since we are losing some information, so this amount of ambiguous information is measured by so-called von Neumann entropy. This is a well-known expression, minus trace rho log rho, and rho A is the previous reduced density matrix. Even though the total system is pure, this entropy turns out to be non-trivial, non-zero, non-punishing. In quantum field theory, so we can define this geometrically. So already cleared in spin chain example. So this is a time slice. So we forget the time is also one direction. And this is a space manifold. And we divide space manifold into two parts, A and B. And you can define this separation curve in orbitally. So we have infinitely many different definitions of entanglement entropy. That means entanglement entropy captures really infinitely a lot of information. So in this sense, this is geometrical. So sometimes people call this entanglement entropy as geometrical entropy. So there are various applications of this quantity as a subject. So first of all, transitional application is original motivation is in a quantum information theory and also quantum computing theory. So there, this entanglement entropy measures the amount of quantum information because this is just a quantum analog of Shannon's information entropy. And recently, this quantity has been also applied to condensed matter physics, especially theoretical aspects. There, one interpretation of this entanglement entropy is a sort of efficiency of computer simulations. If we have some quantum many-body system, we try to approximate this system by using some computer simulation. Then we need to restrict the total Hilbert space of density matrix to finite size. So the important question is how much we can keep the information even if we truncate the system. So this efficiency measured by entanglement entropy. So if the entanglement entropy is very large, it is very difficult to do this computer simulation. So indeed, this quantity is found to be divergent at phase transition point. So at the phase transition point, we have a lot of quantum fluctuations. It's quite difficult to do numerical calculations. And such a point, so in other words, this is a quantum critical point, which detailed also relation to holography has been discussed in a nice talk by Subir Sachidev, this conference. So this quantity is divergent. So in other words, so we can use this quantity as an order parameter, quantum order parameter. We can work just at always zero temperature, but we can change other extra parameter like magnetic fields or some other quantities. So then this quantity divergence, then we know we can detect phase transition. So this is a quantum order parameter. This is an idea recently developed in condensed matter physics. Also, at the same time, this also captures topological nature of ground states. Sometimes ground states have topological degeneracy. Then even though we cannot use correlation function to detect this topological property, we can use actually this quantity to detect topological some non-trivial ground state. This is called topological entanglement entropy. And many works has been done until recently in condensed matter community. Okay, so the basic property of this entanglement entropy is called area law. So in my condition, I'm considering D plus one dimensional quantum field theory. So D is a space dimension and one is time direction. Then there is a universal rule. But here actually, implicitly, I am assuming some ultraviolet fixed point. This assumption is very important in AdS CFT correspondence. And long ago, people like Bomberi and collaborators and Srednoniki showed that more than 20 years ago, the leading divergence of entanglement entropy looks like this. So this quantum field theory includes a lot of degree of freedom. So this entropy actually turns out to be divergent. And epsilon is a UV cutoff. This goes to 0 in the UV limit, or this is proportional to the lattice spacing. So its divergence always epsilon to the t minus 1 inverse, and its coefficient, importantly, proportional to the area of the subsystem, not the volume of the subsystem. So this is the reason why we call this area law. This area law looks a bit similar to the Bekenstein-Hawking formula of black hole entropy, and this was one motivation why people are interested in this quantity. But actually, this is, of course, finite quantity. And, but the entanglement entropy divergence. So its connection is a bit subtle, but people understand, Susskind collaborators understand this sort of loop correction to this formula. But still, this three-level part, finite piece of black hole entropy is missing. Understanding of this is missing. And this is the motivation why we consider and apply a holography to understand some gravitational entropy as an entanglement entropy. So this is a holographic entanglement entropy. And first, I'd like to give the final formula, final formula. And this is actually very simple. This is same as, looks very similar to Bekenstein-Hawking formula. So area of something divided by 4G Newton. So this G Newton is Newton constant in the AdS space. So here I have in mind AdS CFT duality. So the D plus 2 is dual to CFT D plus 1. And we define the subsystem A like this, as in previous definition, and B is like this. We omit time direction. So the boundary of A is very important. So boundary of A is extended into the bulk. So this surface is a codimension 2 surface inside the AdS. And we require this surface is naturally should be, so this boundary of this surface is same as boundary of A. And also this surface is naturally homologous to this gamma A. This surface is called gamma A. So this surface is gamma A. And A is this subsystem. And A is homologous to this gamma A. But there are infinitely many choices of such surfaces. And we especially pick up minimal area, which is minimal area functional takes a minimum value. So this uniquely fixes this surface called gamma A. So we find gamma A and we divide this, we compute this area divided by 4G Newton. This gives a holographic entanglement entropy. And this is a claim, this entanglement entropy is exactly same as entanglement entropy in this dual conformal field theory. So there are a few comments. So in the presence of black hole horizon, this minimal surface typically wraps the horizon. So that this formula actually reduced to Bekenstein-Hawking entropy formula. But this is consistent because we know in AdS CFT, the thermal entropy corresponds to the black hole entropy. So this is a consistent change. Another thing is more complicated situation, like time-dependent space-time. We don't have any nice definition of minimal surface. So because here I implicitly assume some time slice, but it's not, there are no well-defined, uniquely chosen time slice in Lorentzian some time-dependent background. But so in that case, we can actually replace minimal area surface with extremal surface, as I worked with Subadditivity and Nakamura, and we get some consistent result. And finally, this is a recent development, especially. This area formula, of course, assume this supergravity approximation in AdS CFT correspondence. So the next question, what will happen if we take into account higher derivatives? But there are nice developments, especially done by Myers and collaborators, and also Jan de Boer and collaborators. And in general, it's quite difficult. In general, in the presence of general higher derivative, it's quite difficult to find its correction. But especially if we restrict to a nice class called Lovelock gravity, then we can understand how to put this additional higher derivative terms, which corrects this entanglement entropy formula. And I will mention later about the case of AdS5 cross S5. So finally, also, so this, I wrote down some formula, but this, in spite of some heuristic argument or derivation by Forsyth, there has been no, unfortunately, no complete proof, complete derivation of this formula from AdS CFT. However, there has been, until now, so many evidences which support this formula, and no counterexamples known so far. So I write down some partial list of these evidences. So first of all, the area law follows straightforwardly. This is clear, because there is an infinitely one factor here. So every main contribution of this area of gamma A, this is gamma A, is localized here. So this is the area law. And also, for a special case of AdS3 CFT2, there are many known results for two-dimensional conformal field theory. We can use it to compare the holographic result. And this works completely well, especially for one interval case. And as we will also quickly review later, so we can show the very important inequality called strong subadditivity by using this method. And also recently, in a nice paper by Matt Hedrick, there has been shown some consistency between known two-dimensional conformal field theory result about disconnected subsystems. If the subsystem is disconnected, we have some interesting phase transition when we separate distance. And this is consistent, turns out to be consistent with this holographic formula. And finally, so we can have a rather quantitative prediction for the logarithmic coefficient of logarithmic term of this entanglement entropy. So then the coefficient actually turns out to be some anomaly. So in four-dimensional CFT, we have A and C, two anomalies. And in general, they are linear combination of that. And this combination confirmed in both sides, AdS side and conformal field theory side, and they were matched very well. This is done by these recent works. So the one interesting consistency check is strong subadditivity. So strong subadditivity is these two inequalities, this one and this one. So A, B, C is some subsystems, and the assumption is only that there are no overlap between A and B and C. And the topology, I write an explicit example, but the topology is orbitary. So then when we combine A plus B, this means this system, and for entropy for this system, and this B plus C is like this system, so annular system, and always satisfy these inequalities. This can be easily understood in AdS-CFT in a rather geometrical way. So this A plus B is correspond to this region. So this is I projected AdS space into this seat. And this is a boundary of AdS, and this is a bulk of AdS. This is a radial direction. And A plus B corresponds to this boundary. So now I write down some minimal surface, which end up with A and B. So this is a minimal surface correspond to this entropy. And this is this one. And we can regard this some bit this non-smooth one as a surface for A plus B plus C, this green one, and red one is for B. But there are minimal, more really smooth minimal surface, which minimizes area. So this clearly shows this inequality. And second one is obtained by combining different way, and we get easily showed in this way. So this AdS CFT makes this originally algebraic inequality called strong subadditivity, rather geometrical inequality. So I would like to also mention the calculation of this holographic entanglement entropy. So to obtain the analytical result, I restricted to these cases: infinite strip with width L, and this is infinitely long, so this just truncated into large L. This is an infrared cutoff, and the circular disk with radius small L, and their minimal surface looks like this way. So the first case, this infinite strip case, we have two terms. First term is the area law divergence, as I already explained. This is a holographic calculation, so we have g Newton, gravity calculation. So the second term is interesting. This is finite piece, and this is somehow doesn't depend on the cutoff. So we can compare this quantity between holographic side and also CFT side. And especially if we take d equal 1 limit, then this is the AdS3 example. So we get a logarithmic law, and this is C is the central charge, 3 is this just C over 3, and logarithmic L over epsilon. L is the length of subsystem, and epsilon is again cutoff. And this perfectly agree with famous two-dimensional conformal field series that first derived by Holze, Larsen, and Welzek, and recently generalized by Calabrese and Cardi. But here we have a prediction for any dimension. And this is expected dual to strongly coupled gauge theory. So it is interesting to look at a particular case. For example, AdS5 CFT4. Then AdS5 S5 is dual to n equal 4 superamines, SUN superamines. And the previous gravity analysis leads to this numerical result. I write it explicitly. And we can do the calculation in CFT, but strongly coupled limit, of course, difficult. So we just satisfy this free field calculation. Then we get this result. So functional form precisely agree, but this coefficient different. But this coefficient is not protected by any supersymmetry, and this just changes under the change of coupling constant, Tofuft coupling. So this agreement is just same as for third factor in almost same as for third factor, famous factor in thermal entropy by Gabza-Klebanov-Piet. So the next one is this is circular one. If we take circular one, we have many terms because this pick up somehow curvature of this sphere. So d minus 1, this is the area law leading the area law divergence, and this d minus 1. But the interesting thing, the behavior depends on the d is even or odd. So d equal even means this auto-dimensional conformal field theory. We end up with some universal constant, some constant independent of cutoff. On the other hand, in even dimensional conformal field theory, we have logarithmic term. This logarithmic term actually related to conformal anomaly, as we can imagine here. And this coefficient Q is actually proportional to center of charge. In two-dimensional CFT, as already I mentioned, C over 3, and the four-dimensional CFT, and especially if you choose this subsystem is a round sphere, symmetric sphere, this turns out to be 4 times A. And if we distorted this surface, then another central charge called C also appears. But for symmetric case, it's 4 minus A. And another interesting, so this is an auto-dimensional conformal field theory. We have ended up with some constant. And recently, Myers and Sinha shows that actually this constant is some sort of central charge because it shows some, it obeys some C theorem. It decreases monotonically under RG flow. This was shown in a holographical way, not field theory side. But this is quite interesting. So this entanglement entropy somehow unifies the idea of this degree of freedom in both in odd dimension and even dimension. So it is also interesting to consider some black hole case. So in AdS black hole, we know AdS black hole is a finite temperature dual to finite temperature conformal field theory. And in this case, total density matrix is not pure. And there we know that SA is different from SB. This is just general theorem in quantum information theory. And indeed, in the AdS side, so we have a black hole. And this boundary is here, and the black hole is here. So the A is homologous to this surface, and B is homologous to the surface. There is obstruction by black hole horizon, and it is clear they are different. And the explicit evaluation also works well for AdS3 case. And also, so it is also interesting to consider time-dependent case, which is a black hole formation. In this case, we can just start from pure state, and we can do some just unitary evolution. So total entropy, microscopic entropy should be always 0 under unitary evolution. So this means total density matrix is always pure. But we have black hole, so one may be puzzled about this horizon because the entropy is 0, should be 0. But actually, by using, I don't have enough time to explain, but using this entanglement entropy, actually we can show that indeed this is true, even in the presence of this horizon. And furthermore, this entanglement entropy and finite piece of entanglement entropy is like this, shows time evolutions proportional to the black hole horizon. And indeed, this is can be, this can detect black hole formation. In this sense, entanglement entropy can be regarded as coarse-grained entropy. Even though microscopic entropy is always same, but if we take coarse graining, like a thermal gas, we can define entropy, and this is correspond to entanglement entropy, as we showed recently. So now I'd like to now apply this idea to some confining gauge theories and discuss some higher derivatives. So before we go on, I'd like to mention supergravity result, application of this entropy to confining gauge theory. So this is done my work with Nishioka and also nice work with by Klebanov, Kutasov, Mulligan 4 years ago. And this is the basic setup is this Wittgenbach one. So it's n equal 4. We take n equal 4 superamines on a structural surface circle, and which is dual to so-called AdS5 soliton solution times S5. And this solution is just a double rotation of a Schwarzschild black hole, AdS5 Schwarzschild black hole. And this theta direction is now, previously this is a thermal time direction, but now this is just space direction. This is compactified with radius r. So I write here, large r means compactification radius of theta. And in this background is non-trivial, so we can just use the simplest definition of entanglement entropy. We just divide total space into two parts. This is a CFT side. This xt is time, and x and y is this direction. And we just divide this way and half. But still we get non-trivial result. So the calculation in holographic dual side, this is very simple. We just compute area divided by 4g Newton. So this turns out to be this integral is divergent. This is just area law divergent, but we are interested in finite part. So which is given by n is the rank of gauge group, n squared divided by 8r. This is much like Casimir energy, but here I'm talking about entropy. So this is a strongly coupled limit result. On the other hand, we can compute free field theory. Just forget about AdS CFT and just compute free field calculation. Then after summing over Kaldor-Klein mode, after some computation, we get this result. This is a bit different, minus 1 over 12. And this corresponds to Fourier. So as in the previous case, there should be some interpolation between them. But that function is just non-trivial. But it is interesting to discuss some deviation from here, but assuming some some strong coupling expansion. That's what we did quite recently. So this is work with Ogawa, which appears soon. So this is a higher derivative correction to these calculations. So we know that type 2B string theory is R-quadratic correction described by this. This W is a wild curvature. And by using this formula and using also replicatory, we can compute this holographic entropy and correction of holographic entropy by this term. So this turns out to be this value. So this is lambda to the minus 1.5. This is indeed holographic entanglement entropy increases as the coupling gets smaller. This is consistent with the this behavior. So it interpolates between them. So I plotted this here. So this is a point which we are looking at. AdS5 soliton, they are deviates, but higher derivative correction pushes this AdS result towards a bit higher value than towards this Fourier-Mills result. And the extra axis which I write is something, another parameter, which I call twist parameter. So this is this point, the geometry is same as AdS5 soliton. And at this point 1, this corresponds to the supersymmetric background of AdS5 cross S5. So we interpolate by some by using parameter. This is obtained by double weak rotation of the R-charged black hole. So this is extra parameter, and we can see that this deviation gets smaller as we approach the supersymmetric point. And indeed, interestingly, this also gravity gradient also coincide with each other. This is some quantitative agreement about this holographic duality. So also, I'd like to mention that we can also detect confinement, deconfinement phase transition by using this entropy. So this is a holographic AdS calculation. And so there is two minimal surfaces competing. One is a connected minimal surface. Another one is a disconnected surfaces. This connected one is just trivial, this green line. And the connected one is red line, non-trivial. So we always have to get a smaller value. So we get this, so smaller L, we get non-trivial behavior. At some point, we get this way, trivial behavior. So smaller L means UV limit. And the UV limit, we have sort of asymptotic freedom. So theory is close to conformal, so we have non-trivial behavior, but for low energy limit, we get confinement, so trivial behavior. And recently, this kind of calculation also has been done in a lattice calculation. So this is a result by these people and for 4-dimensional SU3 gauge theory. So this plot, the length L is the same, but here they plot the derivative of this, so S. So this means that there are some, this gradient jumps somehow here. So this means that second derivative of S jumps. But here we are taking Largen limit in holographic dual, so derivative of S actually jumps. So there are some this kind of difference. But the phase transition, detection of phase transition looks analogous. So now I'd like to move on to the next topic, and this is actually finite topics. So this is about, to ask the following question: what is a holographic dual of conformal field theory defined on a manifold with boundary? We call this a BCFT. And this means just this picture. So there is a conformal field theory, but with some boundary. So conformal field theory on D score interval or something like that. In CFT side, we have this symmetry. This is duality AdS D plus 1 symmetry, classical symmetry. But we break some part of symmetry to get BCFT, boundary conformal field theory. So this corresponds to AdS D. So there are some this structure inside holographic dual. So this part is cut it out. So it is very natural to think just take standard AdS CFT and cut in some part of that according to some rule. So this gives some induced AdS-D here and consistent with the picture. This setup symmetry is very similar to defect conformal field theory or Janus conformal field theory, but it's actually different because we really cut it out some part of the space-time. Topology is different. So the idea how to consider its holographic dual is like this, which I recently wrote a paper, this AdS BCFT proposal. So as usual, we add some boundary. So this is M is a boundary where CFT is defined. It is asymptotical AdS boundary. And N is sort of AdS space. But we cut it at some point. So this means that we have a boundary for this manifold M. So this means that we need to introduce additional boundary inside the bulk. This is called Q. And we use a standard treatment of boundary, like adding this given the Hawking term. So then the natural boundary condition is Neumann boundary condition. So this requires this KAB is an extrinsic curvature on this surface, and HAB is an induced metric on this Q. So they should satisfy this equation. This is a boundary, some degree of freedom on the boundary energy stress tensor. Conformal invariance requires this TAB is proportional to boundary, sort of boundary cosmological constant, which I call T. So the simplest example is like this. So this is a AdS slice metric of just AdS space. So rho is an extra dimension, the AdS-D is its slice. And the rho minus infinity to infinity, then we just get Poincare AdS. But here I mean just rho is truncated at some value rho star. Truncated at some particular value rho star, like this. Then, so we need to impose the boundary condition here, but indeed this background satisfies previous boundary condition. And by identifying this T, tension of a boundary cosmological constant with this function of rho star. So this is the simplest setup. So there are many interesting observables in this background, but one interesting thing is some quantity called boundary entropy. So this is a boundary entropy. It's first introduced by Affleck and Ludwig. And one definition of boundary entropy is like this. So we take entanglement entropy. So this is half line means there is a boundary here, and this subsystem A is here. And we take this length of A is L, and then we get some logarithmic part, which I already mentioned. Because we cut it half, so this is C, not C over 3, but C over 6. But we have an extra contribution from the boundary. This is identified, or called as a boundary entropy. So we'd like to compute this quantity in this background. So they just compute the length divided by 4g Newton, and we get the logarithmic part, and indeed we get boundary entropies. This is turned out to rho star divided by 4g Newton. And indeed we can do some consistency check, so we can obtain same value from this amplitude. Because this amplitude is same as boundary entropy, and also cylinder amplitude in a high temperature limit. Then we get the two boundaries. Cylinder has two boundaries, so we have twice contribution. So this is just two. We have indeed twice of this. And furthermore, for generic boundary energy stress sensor, if we assume this is boundary energy stress sensor satisfies null energy condition, then we can show the holographic G theorem, which means that this quantity G is a monotonically decreasing function under RG flow. This is very analogous to the similar calculation in C theorem, holographic C theorem. So these are holographic dual of this disk. This is a disk, and this is actually part of a sphere, and the holographic dual of cylinder. So in high temperature phase, it includes also black hole horizon. And we can estimate partition function in this background. Okay, so finally, I'd like to mention some attempt to construct, using this idea, so attempt to construct holographic dual of lattices. So this is something my ongoing work with Shinsei Ryu. And so first, we can start with the simplest model, which is a holographic dual of 2 points. This is actually explicitly constructed, or in other words, 2 qubits. So this is a ADS, some time slice of global ADS. This boundary is maybe, so this ADS3, so I reduce the dimension ADS3, so this is a circle. And the time direction is orthogonal. So we consider A and B is a boundary point. Standard ADS-CFT claims that this boundary is dual to this inside. But here I cut it out, this part, according to the previous rule by imposing Neumann boundary condition. So this green claim is that these 2 points, A and B, is dual to the gravity, which is defined on this green part, which is I call N. And their explicit equation can be written this way, but details are not important here. And so then the interesting quantity is a holographic entanglement entropy. How A and B are entangled with each other? Because I mentioned also this sort of 2 qubits. So how much entanglement appears between them? And if we computed them explicitly, in the end we get this some familiar constant. And indeed, this agrees with boundary entropy. Boundary entropy is sort of degree of freedom in A and B. So this means that entanglement is the same as degree of freedom. This means that A and B are maximally entangled with each other. Okay, so the next thing to do is to put many points, extend this configuration to many points. Then it is natural to guess the geometry looks like this. So many points, this subsystem A and B is like this. Is a sort of spin chain or lattices. Yeah. So we can compute the entanglement entropy between them, and this is a geodesic distance between them, and this takes finite value C divided by 3 times log L. L is a number of lattice points, and this precisely agrees with what we know in spin chain calculations. So in this model, the separation delta x is not important in CFT side, but it's very important in ADS side. So in this sense, this length metric or length appears emergently from this ADS CFT correspondence. Okay, so and I'd like to also comment. This argument looks a bit similar to the calculation framework called MERA. This is a multi-scale entanglement renormalization ansatz. This is first constructed by this Vidal, 2006, and recently its relation to ADS CFT has been discussed by Swinger. And this is some summary of this Swingles paper. So this analysis shows that the situation is very analogous to AdS-CFT. So the idea of this entanglement minimization, we just put many spin chain here. So in the above, we have spin chain here. This x direction, and we coarse grain this. So this another axis is coarse grain direction. In other words, this log z. Z is same as coordinate in AdS-CFT. This is the energy scale or length scale. So we coarse grain this, and at the same time, we disentangle. This means entanglement entropy reduced. This is very important. And the interesting thing is that we pick up some subsystem A, and we can compute the entanglement entropy. Then people find, this condensed matter people find, that entanglement entropy bounded by number of bonds. So we write some curve inside here, and there is many bonds here. And the entanglement entropy is so estimated as some minimum of number of bonds. This is very similar to our formula of holographic entanglement entropy, which is a minimum of area divided by 4G Newton. If this analogy is really true, then this bond corresponds to some unit in gravity. And interestingly, so this spin chain system also interprets some emergent gravity. Now, of course, we have to be worried about radian limit or strong coupling limit thing, but basically, we get this kind of picture. And this is similar, so very closely related to this tree-like structure, so the branching structure. Okay, so let me conclude my talk. So the entanglement entropy is a useful bridge which connects between gravity and condensed matter physics. This means that also this complement to very nice talk by Subadditivity. And so gravity is there, this metric, and the condensed matter system is basically characterized by wave function. So from wave function, we can directly compute entanglement entropy. And also, we show that entanglement entropy is related to area of the geometry, holographic geometry. So this is directly related to metric. So in this way, they connect a condensed matter system to gravity in a nice way. And also, entanglement entropy is a universal quantity in holography. So maybe it is useful to understand the holography in general space-times. So there are several work which we did about holographic dual of flat space and Lorentzian one-fourth, and so on. And so this entanglement entropy is non-trivial even for pure states. So this is a nice quantum order parameter at 0 temperature. And for example, we can use this to detect black hole formation. So under the black hole formation, everything is pure state, but we can detect this entropy, calculating this entropy to show this there is a summarization or black hole formation. And finally, we propose the holographic dual of boundary conformal field theory. And here, the entanglement entropy also again plays a very important role to understand the physics. And also, this holography can also be, I did not mention, but can also be probably useful in AdS-CMT business. And for example, the application of edge states of quantum Hall effect or topological insulators. Or maybe it is interesting to consider some holographic superconductor which localize on this boundary. Also, in time-dependent case, we can discuss non-equilibrium systems with boundary. So where some current flow from one boundary to another boundary. So thank you very much. I think I'll stop here.
You show this proof of subadditivity of the entanglement entropy. Okay, I didn't follow completely, but get the impression that that will be valid for any functional that you minimize. You don't need to minimize the area. You could choose another function and it will still be true.
So which time dependent.
Suppose you define the entanglement entropy as minimizing some action for the surface that is not the area. Will that still satisfy this subadditivity property?
Yeah, right. If we if we have some functional, even in the presence of higher derivative, if we have some functional and minimize it, it is always satisfies strong subadditivity.
So it doesn't show that it has to be the area.
Right.
Okay.
You're right.
On the question of the dual to conformal field theory with boundary, you really should start by asking, in the bulk theory, what is already known about bulk theories with boundary? Because from orbifolds and orientifolds, all kinds of things are known. Also, M theory on a manifold with boundary is understood. So, I mean, instead of trying to invent it from scratch, there's a whole long experience of orbifolds, orientifolds, and other constructions for string and M theories on manifolds with boundaries, which should be the input there.
Thank you very much. Yeah, so to understand microscopic viewpoint, we should start from M theory and string theory. Then, yeah, orange fold and other object probably useful, but sorry, I only consider effective description. So that's a phenomenological approach to that question. But I see. Okay, so thank you very much. Yeah, I would like to think about it.
One example of two entangled systems is an eternal black hole that has two systems on each side. Right. So in that example, once you go to Lorentzian signature, there was a horizon separating the two regions. I was just wondering, in these examples that you have, I would expect also that there is a horizon separating each bit from the rest. Is that what
Yeah, I think so. If we restrict some small thin limit, then it is AdS2. So there are two boundaries in AdS2, they are entangled. That's very similar to this situation.
No, AdS2 actually is not a good example, because in AdS2 you can send the signal from one boundary to the other. I would expect that in these cases you don't.
I see.
You cannot send the signal.
I see. Then in this case, I think we can send a signal between both sides.
No, but if you can send the signal, it's not an entangled system. You have some. You can have operators that don't commute between the two sides.
Yeah, but I'm not sure. Sorry, I'm not sure about it. This is computation just based on computation of entropy. So.
More questions? Okay, let's thank the speaker again.